Another Raoult's law problem. This is an interesting case because now what we're going to do is determine the molar mass of a substance. And this is a very routine kind of a thing where you add an unknown substance to a solvent that you already know the freezing point of, and then you see how the freezing point changes. And once you know how it is changing, then you can calculate the molar mass of the compound. Okay, so that's what this problem is about. Let's go ahead and read the problem. A solution of 2.50 grams of a compound having an empirical formula of C6H5P in a 25.0 grams of benzene freezes at 4.3 degrees Celsius. Calculate the molar mass and the molecular formula of this compound. So we have to calculate two things here, the molar mass and the molecular formula, which tells us that maybe the molecular formula is going to be different than the empirical formula. Remember, empirical formula is the lowest ratio, okay, of all the elements in there. And then of course a lot of data is given to us, the freezing point and then the Kf and all that good stuff. So let's get started. And there's only one formula for us, okay, to begin with. So let's get started with this one, all right? And again, we know the Kf already because that is the constant, and delta T we can calculate because that is going to come from the change in the freezing point. So again, we're calculating for molality over here. So delta T is going to be 5.5 minus 4.3 degrees Celsius, which is about 1.2 degrees Celsius. Okay, and so molality then is equal to delta T divided by Kf, which is 1.2 divided by 5.12 degrees Celsius molality, and so then this we get 0.23 molar solution. Again, this molar solution is moles of solute over kilogram of solvent, and the kilogram of solvent here is benzene, okay, for us. So here's what we do then. 0.23 molar solution is equal to moles over kilogram of solvent, which is 25 divided by 1000, right? So that's 0.025 kilograms. So then moles is equal to 0.23 moles over kilogram times 0.025 kilograms. So the moles then come out to be 0.0058 moles of solute. Okay, so this is where the change is, okay, a little bit from some of the other calculations we've done, because in the other cases we were calculating for the mass. Now we are calculating for the formula, okay, and so which means that the moles is given to us, mass is given to us. Mass is 2.50 grams, and now we just calculated moles, which is 0.0058 moles. Molecular weight is grams per mole. So if this is grams per mole, then all we need to do is divide these two numbers, okay, over here. And so 2.50 grams divided by 0.0058 moles, this is going to be then 4.3 times 10 to the power of 2. You don't have to do it in that. If you want, you can write 430 grams per mole. So that's our first question answered over here, that this is the molar mass, okay, of the compound. So then we are asked to calculate also the formula, molecular formula. So C6H5P, that is the empirical formula. So if you look at the empirical formula and you add that up, which means that you have 6 of carbon plus 5 of hydrogen plus 1 of phosphorus. So by the time you do all of this addition, you will get 108.1 grams per mole. Okay, and this, the molar mass that we just calculated was about 430. So which means that the molar mass divided by empirical formula mass will give us the index, okay, that we need. So which is 430 divided by 108, which gives us 4. So our multiplying index then is 4, which means that the molecular formula is C6H5P times 4. Okay, so that is technically our molecular formula. So that's C24H20P4. That's the second answer that we have. Okay, so these are our answers that we needed to calculate from here. So again, in this one we had an unknown compound over here, and we knew what the freezing point depression was. So once you know what the freezing point depression is and you know the freezing point of your solvent, then you can figure out the molar mass of an unknown substance.